All right, we are now on chapter 15, alternative energy resources. And the first one we're going to be discussing is nuclear energy. So here are some graphs. This one on the right shows our energy usage, just keeps increasing. And then these are projections for years 2030 and 2040. So we don't exactly think we're going to stop needing energy. And this is where we get our energy from currently. So it's still mostly hydrocarbons. All of this is hydrocarbons. And then this little, not quite quarter of this pie chart, nuclear, hydro, and geothermal, wind, and other. So what is nuclear power? It is fission, and that is the splitting of an atomic nuclei into smaller fragments. And when that happens, it releases energy, and then it's like a chain reaction. So when this fissions, then it releases, this is particles and energy here, and then it becomes a smaller nucleus, and then this neutron comes out and hits this other uranium-235, and so forth. And so once you kind of do the first one, as long as you have all these other atoms kind of lined up, then it's a chain reaction. So this release of energy pretty much heats water, can be turned into steam, where it then, generates steam, and you get a turbine. I don't really know all that much about this. This is more engineering. Uranium deposits are usually found in sedimentary rocks, or metasedimentary rocks, so metamorphic rocks that were sedimentary rocks. Um, And it's not because it's forming there or precipitating out. It's kind of like those placer deposits with gold. It weathers from other rocks and just kind of concentrates in sedimentary rocks through like the weathering and depositional process. Um, Minor amounts of uranium are present in many crustal rocks, but granitic and carbonate seem to be rich in uranium. And so carbonate, again, is another sedimentary rock, but granite is not, so that would be where it's weathering from. Um, Extending the nuclear fuel supply. So uranium-235 isn't the only reactive atom we can use. Most of the uranium out there on the planet is actually uranium-238. It's not, I guess, as common to hear about it because it is, if I come down here, expensive and complex. But it's pretty cool because it is a breeder reactor in which when it fissions, and I'm not sure I'm using that, I'm not sure you can use that as a verb, but when it fissions, it converts to plutonium. So it like decays, and I guess that's the word I should use. So uranium-238 decays to plutonium-239, and then plutonium-239 is also fissionable. And so instead of just using their uranium once, like 235, these kind of like you can use it twice. You can kind of use like the the parent and then the daughter material as well. And then it's very common, 99.3% of natural uranium is uranium-238. And then used for over 90% of reactor grade enriched uranium. They have to enrich this. I don't really know all that much about it. Your textbook goes into more detail on that if you're curious. Concerns related to nuclear reactor safety. Well, I guess everybody, obviously, you don't want to be around it, like if it explodes, right? Nobody wants a whole lot of radiation hitting them. Um, However, it says, a lot of them are kind of like you get paranoid, I guess, for no reason. Um, Accidents don't happen all that much. Without an accident, then it's very minor amounts of radiation are released from these plants. Um, However, you can have a core meltdown if it becomes too hot because you lose your coolant. Reactor accident resulting from loss of core coolant and subsequent overheating, creating an unmanageable mass and then migrating out of the contaminant structure. This could result in a catastrophic release of radiation into the environment. Reactors must be located away from active faults because you don't want it to just break. So these catastrophic, I mean, this is like your Chernobyls, right? Nobody wants that. Um, and so I think it was like when they try in the textbook, I think it mentioned when they try to put in like a nuclear power plant, people just protest it because nobody wants it. Like everybody wants nuclear energy, but nobody wants to live next to it. So it's very difficult. Um, Nobody wants to be exposed. Miners, except for like a meltdown, miners are more exposed than anybody else because they're in there mining out these radioactive rocks. And then the tailings as well, these piles, we talked about tailings in, the mining chapter. But they can weather and then mobilize, and then they can be in the water, they can move, just like anything else. And use of breeder reactors to produce and recover plutonium to extend the supply of fissionable fuel poses special problems. And as we have seen in world events, that can be used to make nuclear weapons too. And then what is this? This is the age of nuclear reactors in the world. So the mean age is 26 years. So what is this? Purple is over 41 years, so not very many. Make it to 40. Radioactive waste. Energy produced by nuclear fission produces radioactive wastes, which are difficult to treat. And we currently don't have a long-term permanent storage or disposal site in this country. We talked about that, I think, in our waste chapter. Nuclear power plants are decommissioned once operations cease, and that is expensive to decommission them. Abundant radioactive contaminated material associated with these plants must be permanently and safely stored somewhere, which you need the space and the concrete and everything to store those. Risk assessment and risk projection. No energy source is risk-free. 8% of U.S. energy is supplied by nuclear power in 2021. Nuclear power plants have lower fuel and operating costs than coal-fired plants. And the reliance on nuclear power varies a lot globally, as you would kind of expect, anywhere from 2% in some countries to over 30% in others. So if you look at the chart here, you've got France, Ukraine, Belgium, a lot of European with pretty good, with France is like 69% nuclear. Here we are, United States at 20%, um, which can't be right. That says 8% here. So let me look at this. Nuclear share of electricity generation. Interesting. I wonder what the difference is. And all the way down to um, I guess South Africa, Mexico, Iran, 1%. Um, this one here is just showing nuclear power plants, and how much they are generating in milliwatts here. None in Kentucky. Out west, very few. I don't really know why that is. I suspect maybe it's a lot of water that's needed to cool these plants. Watt in the East Coast. And then there's also fusion, which is like a cool idea, but we can't do it. We just don't. It's going to be expensive, and we don't even have the ability to do it. This is what happens in the sun. So instead of splitting an atom, oh, let's see. I want to see what it says. Combining smaller nuclei to form larger ones. So it's not like it says like what the sun does with hydrogen to make um, helium and stuff. So as you can imagine, it would be very efficient and create a lot of energy, but we can't just like build a sun on Earth is how I think of it. These nuclear engineers would probably laugh at how I'm talking about this right now, but um, it's still very much just a theory. Maybe one day we'll figure out how to harness this potential. And then we will be moving on to solar.